I'm just going to speak to you this morning with a bit of an update on what we've been up to at Thunderhead for the last couple of years, hopefully focusing on the research side of things more than anything. You doing okay over there, Brian? Okay. I'm really not very good at delegating, as my staff can probably tell me. So Brian's taken over running our live stream for everybody joining us remotely, which is actually really cool. I don't know how many of you are aware, but we are live streaming this too. So we have about as many people as in the room joining us every day remotely as well too. So hopefully they're waking up and getting on the stream today. So let's see, I should probably use the clicker. I'll start with just a little bit of evolution of our products over the last couple of years. PyroSim, which is our interface for FDS, has been trying to keep up with the FDS releases that have come out. So 6.5, 6.6, or 6.7, the 6.7 series, I guess, of FDS. There's a lot of things. I won't go into detail over the support for those. Constantly been waiting on FDS 7, so we're trying to prep and be ready for that. And some various other things I'll cover here. For FDS 7, the big issue there that some of you may or may not be aware of is at first they were calling the immerse boundary method, but now they have these geom objects, which are to support more like a triangulated network object as opposed to the old Lego block. And what we've worked on there is supporting that geom record and prototyping it so you can do something like pull in a CAD object and then it will basically, you have some options to convert that into a geom for the FDS file, and it writes out the format of vertices and triangles required to pull that in. That's available preview. If you are working with FDS 7, you can try that out now. We've also updated what we call scenarios in PyroSim, which is kind of a feature that lets you group elements of your simulation for different purposes. Like maybe you need to do a large fire simulation and a small one. You can use the same PyroSim model and enable and disable various portions of the model tied to different of those scenarios so that you can keep them in one place. So if you, for instance, need to change the geometry, you only do it in one file and then you can rerun. Optionally there too as well, you can selectively pick, say, oh, I only want to run 2 or 3 of these, and we, whoops, I think I just went forward too far there. And then it will output also a script file for convenience that you could either use to serial run these, or you could edit the file and run more than one simulation at a time if you need to as well. You can include a variety of different items in those scenarios to turn them on and off, like burners, vents, obstructions, whatever's kind of needed to support those different modeling options. Just one of the noteworthy things that we've added is also support for some of the different more advanced controls. Mathematical controls has come around in the UI for that in PyroSim in the last couple of years. There's a lot of options there that let you take the output of another control device and sort of transform that and get a new value out of it. Mesh partitioning and alignment. Actually, I think Graham worked on this one. He's one of our developers here in the room today. That kind of goes along with running things on the cloud as well, which is one of the features we've brought in the last few years. But often what you need to do is, oh, I need to run this model faster. I'd like to run it on a 32 processor machine. Well, now you need to come up with a way to divide it into 32 even chunks to make that happen. So the mesh partitioner lets you select, say, 2 larger meshes, and then in this case, I've divided it into 8, so it's looking at the cell count based on the relative cell sizes as well, and coming up with a set of 8 meshes that are roughly evenly divided so that you can then split that up onto a different processor set. And that works for, you know, from 2 to 96 partitions each time you're dividing it up. And you could actually continue dividing and get even more partitions than that if you needed to. Cloud FDS is the service that we work with from the CFD FEA group out of Italy that I think runs mostly on the Amazon cloud. But you can submit jobs through PyroSim if you have an account on that, but we've updated that to include their support for newer FDS versions and added some features in PyroSim that let you view the previously run jobs and download the results without having to go through kind of the whole web interface, and then you can open the results in the PyroSim results viewer. On the Pathfinder side of things, there have been a few interesting developments there, a lot of them more targeted around the agent behavior. One interesting one is what we've called internally inferred stairs. Previously, any geometry in a Pathfinder model that was not officially a stair used the level terrain walking speed, so your typical 1 point something meters per second free speed. Where this came into an issue is if, like we saw some stadium models yesterday where it's not exactly a stairway, it's like this multi-connected semi-vertical surface. What we've done is improved the logic inside Pathfinder to detect these sort of lots of single steps strung together and simulate them as if they were a stair, and use the correct movement speeds for up and down stairs. Generally, we find these in complicated scenarios like auditorium or stadiums, or even like an outdoor area that might have various levels. It's not perfect. It doesn't always give you the exact, oh, that's a 7-Eleven stair, but it's very close now to what if you had created your model with an official stair element. It's very close to the answer you would get. Queues we had released and I think talked about at the last FEMTC, but that's been improved a little bit. Primarily the big improvement there is on the visual side. We'd added some things to results viewer, and I think I included an example here. So this is kind of like a little lunchroom plan. So I believe in this one the entrance was over here somewhere, and you come in and there's a couple of drink stations and salad bar, buffet, and then these are the pay stations, and then some tables for eating here. Previously we'd had this set up so that you could simulate it with a queuing system, and our queues consist of like a location where there's a service or something that's going to take you some time, and then the actual queue path to get there. And before, you couldn't see any of this in results. You could tell that the agents were doing what you told them to. But now we have these, you can see the queue paths on the ground. And I think if we play this one also has coloring of the occupants by their current queuing state, so which queue they're a part of. If you look closely enough, you'll see as people move from one to another, their color changes as they approach the next queue. So that's really just a visual improvement, but it helped a lot in sort of making sure the model is acting the way you set it up. This I'll get to in just a moment, but this area is using a newer feature called occupant targets, where people can find an open seat at the lunch table and move on. Attractors is a new behavioral element that we've added, and it's basically an optional behavior setting that lets you modify the current behavior of an agent in the simulation. Basically, these sort of act as side quests for an agent. It's something you want to interrupt their current behavior to do, like, oh, I need to make a trip to the restroom or go to the food stand, or it can even be used in other variety of different scenarios where you may want to just optionally do something else in the middle of your journey. And then there's a set of terminal behaviors, like after you do the side journey, you might return to your main behavior journey, or you might change to another one. The little example sort of running here in the little animation is just, everybody's coming in and waiting, but as they're waiting, there's this optional side journey. Some percentage of them, their bathroom flag gets flipped and they need to go visit the restroom, and then they come back to what they were doing before. So here's a synthetic model. It just kind of looks pretty, but developed just as a test to show kind of how you might use this for museum type behavior. So in this one, if I start it, here comes a couple of agents. They're going to stop and look at things as they come through. And you can use distributions and probabilities here to determine which people stop and how. So you don't have to tell agent A to stop at statue B. It's just sort of emergent. So it can give you these sort of nice, more realistic looking, at least, behavior. Here's just another example of, say, perhaps a waiting room. You've got a couple of, this also uses queues where there's a couple of people that need to be talked to here. This one runs pretty quickly, so we're just kind of zooming through. I've already been buzzed. Was that you, Eric? And these, I don't know if I can speed this one up a minute. Here we go. As they're in the waiting area here, it's kind of similar to the little animation before. Some of the people are stepping off to, I believe, a restroom on the side that we may see here in just a moment. This one runs so fast, this poor guy's going to get whiplash. Oh, vending machines, that's what they're stopping to, or running to do. Every once in a while, a small percentage decide to go get a snack. And then here's an example of using attractors for sort of like the museum case, but in this case, this was modeling, trying to model something like a grocery store. So everybody's coming in here, and then these are the aisles with all of the food and supplies. And so all of the agents have been set to have varying susceptibility to being attracted to things along the shelf. So it's sort of a way to model people shopping through the store. So if we start this one, you'll see a relatively natural behavior. Not everybody's stopping in the same spots. I didn't put in here, the setup of this has little potential attraction spots all along each of these shopping aisles. And then it makes people look like they're shopping through the store. And then they go to the checkout queue and out the door. Occupant targets is what I mentioned a moment ago, like with seating. This helps, it's basically creating a location on the movement mesh where we can direct an agent to go to. And these can be, it's not quite just like a waypoint, it's more of an optional spot. So you can have a set of these open like seats in the conference hall, and agents can be set to go find an open one and utilize it and then move on. And then they can even optionally reserve that seat so that if you're combining it something with the attractor, like the attractor feature I just mentioned, they can move away, do their side, go get a drink from the hall, and then come back to the same seat they were in before. Or optionally, you can have it be, somebody else took their seat when they left it. And you can also set a target priority, and this can be used for seating scenarios, but we didn't really develop a full-fledged ticketing system. So you're not going to send 10,000 people into a stadium and have them all go to their assigned seat. We're not trying to be, Ticketmaster or some service that schedules that. But you can set up a priority field that controls the order in which agents generally fill. So in this example, we've just set that to a central point, and it's sort of just center weighted. So if we have the agents fill in using that priority, they basically fill from the center outward. You can try a variety of different options, like here they're targeting the center of the aisles, and then everybody enters slightly differently. And so here you can just sort of choose your assumption for a space if you're trying to fill it. Again, our goal here wasn't necessarily to exactly show how people have their assigned ticket and they go there, but to get a relatively reasonable assumption of how people might fill the space. I think I have one more that uses a front-weighted. Like maybe this is an open seating at a venue and you want to be at the front. So it may be the most natural of the three. Obstacles. This is some work that has kind of been around for a long time at Thunderhead. I think we first started working on this when we were working with a contractor that was actually trying to integrate some portions of Pathfinder into like a city scale training model for hazards and like emergency response. But the idea of an obstacle is an area in the mesh that can change, come and go over time, but then can either be a blockage or it can represent a slowdown. So it could be a hazard in the space, debris, it could just be crowd control devices. And you can either just use the geometry that you've drawn in the mesh, like the case here, there's just this random polygon. We can either just extrude that up with some material property to look like the obstruction, or you can import other data to represent and be placed where that obstruction is. And then as people approach these, there's various properties for the obstruction. You can either have it slow them down or they can completely avoid the area. So this one, you can just see these come and go over time and people avoid where they are. You have to figure out what you want to do if you make an obstruction appear when someone's in it. And then I think I have a little bit more. Yeah, this is then a variety of kind of combining obstructions. You might have been able to do this in older versions with timing a door and closing it off, but this is representing some barriers that dynamically appear. This is sped up quite a bit here, but you see there's a gate across the escalator, and then we actually barricade part of the stairs. And so it's sort of a combination of both blocking the path for the occupants and adding the visual reference there for the pretty results. Visualization in general. We've continued to improve our lighting and rendering options, mostly around surface textures and colors and lighting of the fire. And we've got a couple of other post-processing elements I'll touch on briefly. Smoke and fire lighting. This one's always just kind of fun, trying to actually use light to color the smoke, so it's not just this black, inky cloud, and then also using the fire itself to reflect onto both the smoke and to the scenery around it. So I have a couple of examples here. Here's a sort of synthetic stadium. We'll light a really big fire at the end of it. Try to burn as many people as possible here. So you see on the left is the without any of the lighting from the fire, and on the right is with the lighting from the fire. And so you see the smoke kind of has this more natural color gradation, and it's a little bit hard to tell here, but if you look, say, at the vertical points of I think the pointer might be losing some battery here. If you look at the vertical parts of the steps, you can see here how they're kind of glowing brightly from this really high-intensity fire, whereas on the left, you don't get that glow. So that's the light from the fire source. Here's another example just in an interior space. This is a little bit unrealistic, but it's got, again, a very bright fire, and you can see it creating the light onto the walls. So it's just an example of showing that actually in work. I think at this one at the end, actually, you can see the smoke come out, and it is quite lit. Everybody needs to get away. It's very hot. Image-based lighting and physically based rendering, those are some terms we throw around probably in our manual a little bit, but it's basically using some more of the technology that you'd see in a game engine or something, where you can light the scene based on an image that might represent a sky or something else and get more accurate reflections. And physically based rendering is where we're using more appropriate surface materials and to get different reflective qualities and material roughness factors. For this one, we have kind of a humorous example. This might be a little dark on this screen. We'll see how it works out. But we put together a Halloween themed video. And what you can notice here is that there's reflections on the floor. And again, the fire lighting, as the fire flickers up and down, is changing the light quality on the scene. And then all of the textures are a lot richer than you would get from a simple CAD model. That one you may have to watch the live stream to really see well. This projector isn't very bright. Proximity analysis. I believe there was a talk, it was at the 2020 FEMTC. Enrico Ronchi and Ruggiero had presented on their exposed framework for an alternate means of quantifying the exposure level in this COVID era, instead of just saying, okay, people are X feet apart or meters apart. It was really quantifying how many people you've come into contact with over time with optional parameters of calculating the distance and that sort of cardinal number of how many people you've interacted with in an integrated sense. So we integrated this into our results processing application to, after the fact, be able to take any of a pre-run Pathfinder simulation and then run it through the algorithms from the paper to come up with a different risk assessment. So in this case, this is just showing some of the outputs that are available. It's showing you the different exposure times. The K values here represent like how many people you've come into contact with and how long. So you can use this to sort of more quantify a more global health risk than just we've kept people 2 meters apart, for example. because every situation is very different. It's very different if you stay a long period of time very close to a high number of people versus a short amount of time and you're farther away. It's an interesting paper to look through and test some of the data. In a similar vein, we improved some of the social distance visualizations that we had been producing. In the past, we could basically, you can infer things like social distance from density plots and density contours, but we created a specific social distance contour and a linkage contour, and they're related. The social distance, what that does is for an influence radius R around every occupant, we basically plot the distance to the nearest occupant, and then that contour plot represents that value of the closest one there. It's a little bit confusing to think about, but it's basically showing for every point on the mesh the nearness of the closest occupant, how close they are to other people. Kind of looks like a Voronoi diagram. I'll show you an example in a minute. And social linkage is kind of the inverse of that. Instead of looking at how far you are from someone, it's how many people you're nearest to, and creating a plot of that. I think I just have one example. This one is of the social distance contour in meters. So the example here is showing that, for instance, these people in the orange, they're in about 1.5 meters from one another. You can see these change over time. It's kind of get this sort of Voronoi effect. But this was from a validation to make sure we're getting the right answer that we put in to the Pathfinder social distance modeling. 360 video export. This is something that we had added as sort of a mini VR. We've supported VR through like an Oculus headset for quite a while. But what this export does is creates just a standard movie file that you can upload to YouTube. It's kind of like an MP4 format. But then it can be viewed in a VR headset or with a phone-based virtual reality like the Google Cardboard, where you put a high-res phone, and I don't think those really gained much traction. But also on YouTube or other video viewers, you can view this 360 full spherical video and look around. And what this allows you to do is share results like from Pathfinder or PyroSim with other people who don't have the results viewer for those applications, but they can still look around and they don't have just a fixed static image. And it can either be from a single location where you could look around, or it can follow the camera path. I think we set this up. Eric created a big click here. See if this works. So this is that same little bit too dark Halloween video, but now if I click, I can actually look around. And so you can put these up on YouTube. So maybe it's not a spooky Halloween haul, but maybe it's your stadium and showing the exit path. You can then, basically you're exporting an infinite amount of views for the client rather than just one fixed viewpoint. Flip back. There we go. Other research that we've been collaborating with and working on internally. The last couple of years, we've been involved with the IMFSE program. If you haven't heard of that, I encourage you to look it up. It's an International Master of Science in Fire Safety Engineering. There's a group of universities involved with that, which now off the top of my head, I don't know how many. It's managed through Ghent, I believe. We've been a program contributor for the last year or so and tend to be for a while. There's, I believe, around a dozen corporate and nonprofit sponsors, and then they've supported, I believe, 30 or 40 graduate students so far. So it's a way to support graduate work in this field, and you get some coordination with what the students are doing. And we participated in the FSE Day this year. A representative from Thunderhead presented on wildland fire modeling. We spoke a bit about FDS and their terrain options and level set wildfire modeling with that, just to give the students an exposure, because they're from all backgrounds. They're not all modelers. So that was interesting and worthwhile to have that feedback with those upcoming researchers. We have a variety of other ongoing collaborations going right now. We've working with Anne and Steve. She's the University of Edinburgh. They are working on a project with quite a few coordinators on first responder communication and the social psychology oriented around that. I don't know if Steve's going to talk about that some. He said Ann was going to say something, so I suspect we might hear a little bit about that. Also at GHD now is Pete Thompson, who used to be working with AutoCAD. There's work there I think we'll also hear today from my last bullet point there, Nazim, but they're continuing work with Building Smart and creating these model view definitions that can work to push data back and forth. Actually, we saw Nazim's talk yesterday, didn't we? Push data back and forth between simulation tools and the BIM tools like Revit. And we had worked with Nazim on that, helping provide a little bit of work in Pathfinder to help him test and validate the work that he was doing on those model view definitions. We are also thinking about working on APIs inside of Pathfinder. We already have some scripting engines that we've worked with some people. We're in some discussions and with the research group at ULIC and seeing if we can open up Pathfinder for, this is ongoing and we're looking for feedback on this, but if we can open up Pathfinder in some way that might be of use to the research community and see what kinds of synergies we can develop there. The concept would be a framework that would allow researchers to try different models or various behaviors, but while also allowing our users to do more advanced things than they could through the model itself. I know in the past we've worked even with some scripting with Tomas here at Recognity, like to get more advanced behaviors. I believe at the time he was modeling a vaccination clinic. Internally, we've been continuously working a little bit in background on trying to improve cross-flow and counterflow, which is one of those really tricky problems. There have been some really good experimental data out of ULIC where they had a bunch of students walk through these intersections. We've been testing some alternative methods on collision and avoidance. But the big thing there is we've started to get more quantified about it rather than, oh, this looks a little bit better, but to try to figure out if we're actually making things better or worse. So what we have here is just an intersection with people coming from two directions. And on the left, what we have here is in older versions of Pathfinder, you can see how things get kind of stuck and at a lower flow rate than they would in real life. So this is what we really would love to fix. In the center, what we have is results from the actual experiment. And you can see it still does slow up. There's fewer people leaving than entering, but you sort of see these waves move through and what we almost internally call, people are moving in the wake of the person in front of them. Somebody sort of starts a path and then people follow. On the right here, what we have is an internal test version that kind of is starting to get us there. We still have too much backup, but we're starting to see that behavior of the right angling of these folks upstream in the flow and then the following in the wake behavior. So that's in the right direction, but to help us determine whether we're getting there, we've developed a score to compare these. And basically this works on any contour that has been generated out of Pathfinder. So this could be density or any of the various measures that we can output or calculate from our contours. And you can take those two contours and basically create a kind of a sum of the squared difference and then use that as a metric to determine how different two runs are. So this could even be used in, and we may start using it internally to validate internal, like maybe you run two PyroSim models and you're looking at a temperature contour. You can validate that you've gotten the same answer between the two by looking that they have a zero score between the two contours. So here's just that same set of models, and you see in our old version, this is a plot of what we call usage, which is an accumulated over time. How long has that spot been occupied? So it's sort of like an integrated density over time. And so, we have too many people hanging up here for too long, and the real model, people get through faster, and we're getting closer there here, but not close enough. So if we compare, this might be a little bit small, but the score is 27 here from our old version compared to the experiment, and it's 18 to compare the proposed changes versus the experiment. Certainly we'd like to drive that closer to 0 to say, okay, now we're matching that experiment. But that's kind of the concept we're working on now to help guide our internal development changes. We're also working right now, this is a little bit outside the evacuation side, but back maybe more to the fire protection side. We've been working on a user interface for the CONTAM model, which was written as a contaminant transport simulator. It's a kind of a zone, you have regions connected to other regions. So it's sort of a zone-based model where you have a pressure zone and flow paths between them, but it's widely used, particularly in the United States, for pressurization study work. So people are looking at making sure a stairwell or elevator shafts have the code required pressure difference. So we're currently prototyping that, making pretty fast progress, but we would certainly be interested to know if other people are interested in this work and have feedback in how they're using or how they're applying and doing pressurization studies, whether they're using CONTAM or something else. So I'd encourage anybody to reach out and talk to us if you're interested in that project as well. I think that's about the last. I don't know how I did on time there. I'd like to thank everybody in our group. There's been a lot of work from a lot of folks. We've been at this for a while now. I think 2011 was the first FEMTC that we helped organize after it stopped happening at NIST. And at that time, we probably had 6 people on staff. And now we're at about 3 times that. But it's a great group of folks, and they're really doing good work. Just wanted to recognize them and their work. With that, I'll stop and ask for some questions. Are you going to play? I guess you're running the work. I'll just ask for questions. Anybody have any questions? Comments? No? Ready to move on to Steve? That's fine too. Yes? Yes? I'm not familiar enough with the CONTAM. The question was whether the pressurization model took into account the piston effect of elevators. I'm not sure is the answer for that one. So. The CONTAM work is all published on you should be able to search it on the internet. It's a NIST tool that's been around for a long time. So, any other questions? No? Okay. Well, next up is Steve Gwynn, I believe. Oh, in the back, Moshin. Sure. I'll be back there.
Check.
I'm interested more in this score that you showed. I don't know exactly what kind of behavior do you measure with it. Is it like the stripes, formations? Is it like the distribution of the density? There are many things that you can say, oh, if it's 0, then we got the experiment right. But what exactly did you get right with this score?
Yeah, good point. Yeah, and I wasn't trying to imply that if we got a 0 on that score that we had the right answer. That is a really big challenge with things like that intersection model. How do you determine that you have people moving in the same general behaviors, like whether it's a lane-forming behavior or other high-level, and that's kind of a challenge. That is a research challenge of figuring out what it is you should measure. That's why that was just a first step that was a useful one, is looking at that accumulated usage, because at first we thought, oh, measure the density over time or the flow rates, right? And those you could have the right flow rate going in and out, but entirely the wrong behavior at the intersection. So yeah, there's a challenge there to figure out what exactly you should be measuring. But that's why we implemented that score based on just 2 contours as generated by the Pathfinder results system, is because then you could pick anything you want and just get a comparative score for that measure. So I think in the end, you'd like to have probably a set of measures that say, okay, I think if you have this, measuring the fundamental diagram before and after the intersection over time, adding that along with, density or usage measurements, other things, or even just comparison of paths themselves. But good question, thank you. Anything else?
Information score,
Certainly. Exactly, exactly. That's the concept. So. All right. I'll yield the floor to Steve. Thank you.